Hi, today I'm going to talk about Ptolemy theorem. Ptolemy theorem is about the product of two cross-diagonal AC times BD equals the product of the size AB times CD plus product another size of BC times AD. This theorem first discovered by Ptolemy in his creating of the table of chord. Ptolemy is a really famous Egyptian mathematician. He born in Egyptian poverty of Roman Empire, but he lived most of his life in Alexandria. He's most famous of his work in mathematics, astronomer, and he also is very famous geographer and poet in that time. He wrote two books in his entire life. The first book is Unjust, and the second book is Primary Hypothesis. Before we're going to the theorem, I want to talk about some terminology we're going to use. First is chord. The chord is if you have 2 points on a circle and you connect these 2 points, we call that chord. For example, DC is a chord. If you have two chords here at end point, we call that inscribed angle. For example, the chord DC and the chord BC is here at the end point of C, so we call the angle DCB is an inscribed angle. If you have two inscribed angles create a quadrilateral and inscribed by a circle, we call that isosceles quadrilateral. When we have isosceles quadrilateral, if the two inscribed angles subtend the same arc and their measurement are equal. What I mean by that is if you have inscribed angle ACB and we have another inscribed angle ADB, both subscribe the same arc AB, their measurement equal. The way we prove that is, as this graph shows, there's an inscribed angle ACB and the R is the center of the circle. As we know, the angle ARB equals the arc of AB, and we can see the center of R divided by the inscribed angle ACB into a smaller triangle, which is ARC and the BRC. Since in the angle ARC, since the two sides are equal because they're both radius, we can assume ARC is isosceles triangles, which means that the angle of these two sides are equal, and this angle equals 180 minus 2x. In the other side, the BRC, similarly, since the two sides are the radius of the triangle, which means these two sides are equal, this angle right here equals 180 minus 2y. As we know, the circle itself is 360 degrees. 360 minus 180 minus 2x minus 180 minus 2y equals 2x plus y, which is the angle of ARB. And also, we show since this angle is x, this angle is y, ACB is equals x plus y, which is half of ARB. So ACB equals half of the arc of AB, which shows ACB equals ADB.
All right, so a concept that we're going to have a good grasp on for proving Ptolemy's theorem, which we talked about in the other video, is the concept of similarity, especially when it applies to triangles. Now, similarity is a very simple but powerful concept. For example, take these two triangles, ABC and XYZ. Now, these two triangles are similar because they have the same shape but different sides. We did note that with this little tilde here. ABC is similar to XYZ. And now we can tell if triangles are similar two different ways. If their angles are equal, here we would have angle A equals angle X, angle B equals angle Y, and angle C equals angle Z. Now, because triangles have a total of 180 degrees inside of them, if we know two angles, we can figure out the third. So we only need to know that two angles are equal to tell if they're similar. This is called the AA or angle-angle criterion. A reminder of a couple of concepts we're going to need in a minute. If you have a quadrilateral ABCD, if you have, say, that AB is parallel to DC and AB is equal to DC, then ABCD is a parallelogram. And the other thing is if we have two parallel lines here and here, and we have another line crossing both of them, which we call a transversal. These two angles here are called alternate interior angles, and we have that they're equal. Angle Q equals angle R. All right, so the big theorem that we're going to have to prove for Ptolemy's theorem is this one right here. If we have two triangles ABC and XYZ and they're similar, then we have the following ratios for their sides. We have AB over XY equals BC over YZ, and AC over equals AC over XZ. Before we prove that, we're going to talk about this lemma here. A lemma is basically a less important theorem. This says that if you have this setup here, triangle ABC and this line UV, then if we have UV and BC are parallel, that is equivalent to saying that AU over AB is equal to AV over AC. All right, to start with the proof of this, we're going to define a couple of symbols here for convenience. What it's going to say, we're going to say that alpha is equal to UV over AB, and beta is equal to VC over AC. Okay, to start with, we can immediately write that AU here is equal to AB minus UV, and using our ratios here, we have that that's equal to 1 minus alpha times AB. The same way, we can say that AV equals AC minus BC equals 1 minus beta times AC. If we divide these two equations up, we have that AU over AB is equal to 1 minus alpha, and AV over AC is equal to 1 minus beta. Notice this is the same ratios we have up here. So if we can show that alpha and beta are equal, then we have the same expression up here. So that's where the direction we're going to go. All right, here K denotes area. The subscripts tell you what triangle it is the area of. So the area of triangle BUC is equal to 1/2 the base UB times its height. And the area of triangle ABC, the large one, is equal to 1/2 the same height times AB. If we divide the area of triangle BUC by ABC, we get UB over AB, which is what we defined alpha to be. And if we divide the area of KBVC and KABC, we get BC over AB, which is equal to beta. Now, we wanted alpha equals beta. When that will happen, if these two ratios are equal, notice they have the same denominator, so we need KBUC and KBVC to be equal. And those are these two triangles here. Notice they have the same base BC, so we need their heights UE. All right, so we've taken this expression of the lemma here and changed it to saying the following, that if UE is equal to VF, that's equivalent to saying that UV is parallel to BC. All right, so we'll prove one part of this by saying that if UE is equal to VF, if these two are equal, then we have that since both of these are heights of triangles sharing the base BC, they're both perpendicular to BC, therefore they must be parallel. Now if we have these two lines being equal and parallel, then we have that UEFV is a parallelogram, and therefore we have to have that UV is parallel to EF, or that UV is parallel to BC. Now, let's reverse that and say we're going to assume that UV is parallel to BC. Well, clearly that's the same as UV being parallel to EF. And then, again, we have these two heights of the triangles sharing the base BC, and so they must be parallel. So we have two pairs of parallel sides, which is the definition of a parallelogram. And so, since opposite sides of a parallelogram are equal, we have that UV equal to VF, which is equivalent to this right here, which we were trying to prove. All right, now that we have that out of the way, we are ready to prove our big important theorem right here. All right, so we want that given two triangles ABC and XYZ are similar, these two here, we want to show that XY over AB is equal to XZ over AC. All right, two cases here. First, let's suppose that xy is equal to AB. Well then, since we have similar triangles here, their angles are equal. And so we have a equal side here, so just using our angle side angle criterion for congruence, we can say that ABC and XYZ are congruent. If we have that, then XZ is going to be equal to AC. So using these two facts, we can say that XY over AB is equal to XZ over AC, which is equal to 1 in this case. Second case, let's say that XY is not equal to AB. Well, then let's choose a point U on AB so that AU is equal to XY. And let's pick a point V on AC so that UV is parallel to BC. Okay, so we have angle AUV and angle B here. Since these are parallel, we have alternate interior angles here, so this and this are equal, which we have here. And since we have similar triangles, we have that angle B here is equal to angle Y. Similarly, we have that angle AVU is equal to angle C is equal to angle Z. Okay, so now we have these facts here. We have AU is equal to XY. We have angle AUV is equal to angle Y. We have angle AVU is equal to angle Z. So using our side angle angle criterion, we have that triangle AUV is congruent to triangle XYZ. So using that fact, we have that AV is equal to XZ. Okay, we have that UV is parallel to BC. And so from our lemma here, we can then say that AU over AB is equal to AV over AC. All right, and taking these bits of information that we've gathered, we can combine them algebraically and come to the conclusion that XY over AB is equal to XZ over AC, which is precisely what we were trying to prove here. The math is exactly the same for these other ratios, so by proving this, we've effectively proved it for the other ratios. And so we're done here.